All right, I'm back. We're on page 299, and we're going to keep going. We've been talking about the power rule, how you can use it. Differentiability implies continuity, whereas continuity tells you absolutely nothing about differentiability. So a lot of ideas. So let's see what we're asked here. So we are given that the function f is differentiable for all x, where x is not 5, sketch 3 possible graphs of f prime, the derivative of f of x. This is interesting. So we're going to sketch f prime based on the fact that the function is differentiable everywhere except 5, which means the derivative exists everywhere except 5. So we have like an infinite number of options. I'm just going to go through a couple. So maybe, let's say, so 5 is a problem. So maybe the slope is like 2 until you get to 5. And then maybe the slope will be -1 after 5, right? So this could be what f prime would look like. If that's what f prime looks like, though, how many of these am I supposed to do? 3? All right, I'm going to try to squeeze this in. If that's what f prime looks like, then what does f of x look like? Well, we don't really know, because we don't know if f of x is continuous at 5 or not. We just know that the slope will change instantaneously from +2 to -1. So potentially, we also have no idea about like y values. We don't know where they are at all. So a +2 slope could look something like this potentially. -1 slope could look something like, well, it's got to be like less steep, I guess, like this maybe. But it could also like connect, because we just don't know. It could be like an almost absolute value where the slope is +2 on one side and -1 on the other. So it's like a little broken, but absolute value-ish, esque, I think is what I was going for there. But we don't know. So that's one option. What's another option? So another option, you could go positive, positive. I think this is an interesting proposition though. So at 5, I'm going to put in a vertical asymptote. So this is going to be f prime. What if f prime kind of, what did I do? Oh, wow. I like somehow opened up a second version of these notes at the same time. I don't know how I did that. That was weird. I'd almost like to do that again if I could, but I don't know what I did. All right, so I'm going to say like this, and then like this. What do you think happens on the graph of the original function if the graph of the derivative has a horizontal asymptote? So over time, the slope of the function, which is the derivative. So over time, the derivative approaches a finite number and stays there forever. So like this graph that I just drew, the limit as x approaches -infinity and infinity of f prime is 0. So what do you think that means for the original function? Well, if you get 0, that means over time the slope of the original function approaches 0. It must kind of approach a horizontal line, right? Because that's the sort of thing that has a slope of 0. That's another thing. You just have to like think about all these things, and it's a lot to think about. And if no one's telling you to think about them, I don't know why you would think about them, but like think about that. So here, what could this look like? Well, all right. So as I approach 5, the slope has to go to infinity. So that's weird. As I approach 5 from the left, the slope has to go to infinity. So what would make that happen? Maybe this, right? So imagine a tangent line riding along this curve. That's what I always think of. Like you got a tangent line, you got a little point, and the point's going to be moving to the right. And then like, what's going to happen to the tangent line? As you get closer and closer to 5, the slope of the tangent line goes vertical, goes to infinity. And then we could also have it kind of go like this. So I think that this is what that graph could look like. And if we had a tangent line on this side, then as x goes, so as you move to the left, sorry, I confused left and right there for a second. As you move to the left, as you move toward 5, that tangent line is going to tilt, 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 and it's going to have like basically an infinite slope. It's going to go vertical. So I think that's another option. I don't want to totally belabor this. So another thing that we could do at 5 is I'm going to do an asymptote again, but like a different behavior at the asymptote. So maybe something like this. Okay, so I need a function that as I approach 5 from the left, the slope will go to negative infinity, which like this, right? Tilt to negative infinity. So let's see. I should watch some of these videos and see if anything that I do is even like visible. I don't even know if it is. Slope has to go to negative infinity. All right. And then as I approach 5 from the right, the slope has to go to positive infinity. I think it's going to look like this. Like that. And then like that. So this is called a cusp. A cusp is a point where, so we had a sharp turn. That's where the limits of the derivative from the left and the right are finite, but not the same, right? So the slope from the left could be 5 and the slope from the right could be -2. Slopes are finite, but not the same. If the slopes are infinite, but not the same, positive infinity, negative infinity, you get what's called a cusp. So this graph has a cusp, and I think that's good enough. Let's take a look at this problem. So given that f of x equals the quantity x minus 1 to the 20 over 19 plus 2, show that f is differentiable at x equals 1 by finding the derivative on your calculator and comparing domains. All right, that's a good thing, because I was like, how are we going to find this derivative? All right, so let's start with the domain of f of x. So f of x is like totally normal, right? It's you're finding like essentially the 19th root, so that's an odd root, so all reals. So the domain of f of x is x is an element of the reals. All right, let's have the calculator find the derivative for us and go from there. So pop over to the calculator. I'm going to start a new document. F of x is quantity x minus 1 to the 20 over 19, which is kind of weird, and then plus 2. Okay, let's have the calculator find the derivative. So template, and then find it. X is the independent variable, so you punch that in, f of x, press enter. All right, so it actually looks like you used the power rule here. You didn't. Use something else. Don't even worry about it. I'm not going to ask you to do anything that you can't figure out from the rules that we know, so don't worry about it. But it looks like we used the power rule. We kind of did, but we didn't exactly. But anyway, what is the domain of this? So one option is to look at it and think like, yeah, the domain is all reals. Another option is to ask what the domain is, where x is the variable. All reals. Okay, so let's go back to the notes and we'll fill that in. So the domain of f prime is all reals. I didn't write down what I'm not going to write down what f prime is, but we saw it. You know what it is. So let's see. Domain of f prime of x is x is an element of the reals. So since they have the same domain, that means the function is differentiable. If the domain of f prime was like all reals except 3 for some reason, then it wouldn't be differentiable because f of x exists at 3, but f prime of 3 doesn't exist, not differentiable. So therefore, f of x is differentiable. Actually, did I answer the question? Yeah, I mean, it's differentiable. So differentiable, therefore differentiable at 1. You always got to make sure you answer the question, which is not always easy in calculus because like the questions kind of like fly around. There's like a lot of questions in any one part. See if you can zoom in, make it locally linear. All right, let's go back to the calculator and see if we can do that. So we're here, and I defined f of x, right? So I have that. So I'm going to add a graph page and graph f of x. So I want to make it locally linear, so I have to zoom in. So zoom in, and no. I mean, the answer might be that the calculator is not able to do this, but it should be, because we know that eventually it should turn into, it's not really zooming by very much, I think, unless I'm going the wrong way. Are you flattening out? I want to go really fast, but the problem with that is that you see how I'm not getting exactly, I got it. If you get exactly the kind of like vertex-y point of this thing, it does this really annoying thing. Was I zooming the right way? I hope so. it does this annoying thing where it's like, oh, did you want to change the function? Like, no, I didn't want to change the function. So I'm going to just chase it. Chasing. Is it flat? Oh, did I zoom in as much as like humanly possible? I zoomed in as much as you could. The calculator can't even show it, but we know that the derivative exists there. In fact, let's do, let's evaluate at x equals 1. And we get 0. So the slope is actually 0. There's actually a horizontal tangent line. Let's see if we can get the calculator to give us that. So the calculator, if you do menu 6, menu 8, points and lines, and then option 8 for me is tangent line. So I'm going to click on the graph, and then I'm going to do something a little weird. So you can like grab this and move it. At the minimum, look at that. At the minimum, it tells you that the tangent line is y equals 2, which means that definitely this thing has a slope of 0 at that point. But the calculator just can't show it to you. That's why we need to learn all of these things that calculus can do, because otherwise the calculator can't always show us. And then what do you do? All right, back to the notes. The answer is you cannot zoom in enough, but you should be able to. I bet GeoGebra can. I bet Desmos can. Calculator is a little limited on that one. All right, so this is just a summary of some things. So we have derivative at a point is f prime of a, derivative as a function. You typically use the limit as h approaches 0. Tangent line, secant line. We know the power rule. We know the sum and difference rule. We also know the constant multiple rules. That's just a summary of the things that we know so far. We also know a lot about increasing, decreasing. We've talked about concave up, concave down, maximums, minimums, just like so many things. But these are the like, make sure you have these memorized so far type things. And I will be back in the next video to do even more stuff. So I will see you then.